So when lambda is greater than 0, it goes up. Yeah, it shoots up. Yeah. It shoots up like that. Okay? This is bad. Actually, we don't like to see this. We wish to see things, converge and smooth, and it doesn't explode. So if you see something like that, this is a typical unstable behavior. Also, if lambda is equal to 0, then it's just like it's a constant. This is yeah, it's an exponential function. You will see this very often. Right. Exponential function. So we have some rough idea about signals. Let's now look at a system. System processes signals. So we often use a block like this to denote a system. And then you have those are signals, those arrows are signals, those lines, these arrows are signals. Then these are we call this input signals, the output signals. In general, a system might take many input signals. So if you write it in this way, you see that you have a U1, UM. Those are all signals going in. You also have output signals going out. You have M of those input signals. You have P output signals. Right? So if indeed this M is greater than 1, P is also greater than 1, then you say, well, this system has multi-input, multi-output. Then it's a MIMO system. So in the case of MIMO system, you put all the inputs in a vector. In the vector, you use like a UT. So this U is different from this U. This is a bold U. So you see it's darker, thicker. So we use a darker and a thicker symbol to denote a vector. Okay? So it's a vector signal. Similarly for Y, you have a darker Y. So this is a bold Y. And the signal basically, with the input-output relation of a system, we write this way. So you take a signal and put it in the system, and then the system is going to generate an output. Right? So basically, you take a signal, basically a time function. It's a whole function. Okay, you send it to like a processor. This system can be considered as a processor. It's like a black box. You don't really know what's going on inside. Right? You send it in, and in the other end you have something coming out. So that's the thing coming out, of course, is called the output. Notice that this system takes a whole signal as input, more than just a value. It doesn't take just 5, but it takes a sinusoidal signal into the system, and generate now probably an exponential signal. It doesn't generate like a 10 or a number. Okay, that's something you have to keep in mind. It's different. The system is different from a function. Function is that you give a number, then the function generator is going to give another number out. That's a function. So the system is actually more complicated. It takes time function and gives out another time function. Okay? We have talked about we have to count the number of inputs and outputs in the system. If indeed the number of input is 1, the number of output is also 1, in that case we say the system is single input, single output system, SISO system. Actually, the main focus of this course is in SISO system. So this is the first course in control, so it's an actual introduction. Introduction to control stuff. So we look at simple case first. Of course, you can have a more complicated case. In general, you have a MIMO system. MIMO system nowadays, of course, most of the system later on, I mean, in the future, maybe it happens that you're working Boeing, you're working Boston Dynamics. All these companies, those are robotics or whatever. They have a MIMO system. So it's the control of MIMO system, of course, requires more knowledge, more like experience. So later on, you're going to worry about that. If you go to graduate school, right, to study the control of those things, then you'll learn more about MIMO system control. So this course, I'm going to start from the basics. SISO systems. Occasionally, like this and this something in the middle. If there is one output or one input, and you get some kind of system which is a bit more complicated than that, but less general than this. Well, occasionally we deal with that kind of systems, but again, it's not much harder than the single system. Therefore, all kinds of systems. Let's again look at some very simple, typical ones, and get some kind of feeling how to classify systems in different ways. Previously, we classified systems according to SISO, MIMO, and things like that, right? That's one way to classify. There's also some other ways to classify. The simplest system is called a static system. System without memory. So in this case, well, if we have a U in certain waveform, the output is, well, the output has the same waveform. It's just like a scale it, amplify it, or scale down a bit by a constant. So this system is called a proportional system. Proportional system. Simply called P system. Memoryless, static. That's too simple. Actually, this is just like an amplifier. Whatever you have, whatever input signal I take, I just multiply a constant and send it out. Too simple. Not we need to use it, but it's not exciting. Dynamic systems. Well, dynamic systems, then that makes the whole theory interesting, and of course, non-trivial systems are all dynamic systems. the simplest example of dynamic system is integrated. Or simply I system. Integrator is that you take the input and then integrate it from minus infinity to t, and it gives out the integration gives the output. You see, of course, this system has memory. What happens in the past is going to show up. Show up in the interval, and it's going to give you some kind of different value at any particular time. Possibly you have a gain, you have some kind of a coefficient here in I. So according to whether you have memory. Another way is according to whether you have or according to this so-called causality. So what do you mean by causality? A system is said to be causal if the output value at the same time does not depend on the future input. Okay? Basically, it doesn't have some kind of a prediction. You cannot predict the future. So all physical systems are like that. If time goes in one direction, you cannot go back. Right? So you can have the past input affect your current output, but the future input cannot affect the current output. Okay? So that's the concept of causality. This is causal. This is also causal. But this is just simply no memory, of course, it's causal. The current output value depends only on current input. It doesn't depend on the future, doesn't depend on the past. So that's a simple situation. Of course, that's called causal. So this integration, this is an integral system. The output depends on the past input, and of course the current input, but not the future input. And this is causal. This is the integrator is causal. So this is causal. So if we put this a P system and the I system together, add them together, then you get a PI system. Non-causal system. Well, something the output of system at this particular time depends on the future input. That sounds strange, right? Indeed, that's strange. Well, no physics system like that. Although maybe in your signal process, in your whatever course, you say okay, you can do non-causal